Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to gently explore one of the most mysterious and beautiful journeys ever undertaken by humanity. A silent, almost forgotten odyssey that continues to unfold light years away. We'll be drifting through the vastness of space, contemplating the quiet perseverance of two small explorers and asking, what does it truly mean to reach beyond our grasp, to send a whisper into the cosmic silence, hoping for an echo? But don't worry, we'll take it slow. This isn't a race through equations or a lecture on astrophysics. It's more like floating through a galaxy of ideas with a cup of chamomile tea, allowing your mind to wander and gently wonder at the profound beauty of the unknown before peacefully drifting into sleep. So let's begin our soft descent into the stars, back to a summer that pulsed with quiet ambition, the summer of 1977. Imagine that summer warm and full of possibility when NASA's Jet Propulsion Laboratory, a quiet hub of brilliant minds, prepared for a launch that seemed at first quite modest. Two towering Titan Centaur rockets stood ready, each cradling a nearly identical spacecraft, known simply as Voyager 1 and Voyager 2. These weren't just sophisticated machines of metal and wire. They were distilled hopes, encapsulated questions, set to embark on a journey designed to peer into what lay beyond the comfortable confines of Earth's embrace. Their initial purpose was remarkably focused, a 5-year mission, a blink in cosmic time. They were built with the intention of studying Jupiter and Saturn and their larger enigmatic moons to gather whispers of data and send them back across the vast expanse. Picture them as tiny brave birds released into an immense ancient forest with the sole hope that they might return with a few seeds from trees never before seen. Their task was to gently caress the gas giants with their sensors, to listen to their ethereal hums, and to send back faint coded messages that would reveal the secrets of these distant worlds. The sheer audacity of such a venture even then was breathtaking. To launch something so fragile, so delicate, into the brutal vacuum of space, expecting it to survive for even half a decade, was a testament to human ingenuity. But now, let's allow our minds to settle on the most extraordinary detail, a truth that unfurls itself like a quiet miracle. Nearly 45 years later, far, far beyond that initial humble 5-year expectation, NASA is still in constant, unwavering communication with both of these resilient probes. This isn't just a fleeting connection. It's a living, breathing dialogue across billions of miles. These twin silent Voyagers still routinely receive commands from Earth, gentle nudges in the dark, and in return, they transmit precious data back to Earth's deep space network. Consider what this means: a continuous thread, gossamer thin yet unbreakable, stretching across the unfathomable distances of our solar system and beyond. It's like a soft, persistent hum, an unbroken conversation that has outlasted generations of computers, changed countless human lives, and redefined our understanding of time and distance. This enduring connection makes Voyager not just a successful mission, but the longest-running mission in the entire history of space exploration. It's a testament to the idea that sometimes the most enduring legacies are those built not on grand, immediate declarations, but on quiet, persistent resilience. Imagine the quiet dedication of the teams on Earth, receiving these faint signals like listening for a heartbeat from across an ocean. Each data packet, each telemetry whisper, is a small triumph against entropy, against the vast, cold indifference of space. It's a rhythmic, almost meditative exchange, a constant pulse that reminds us of the profound link between our curious minds here on Earth and these intrepid machines far, far away. The concept of a machine outliving its creator's immediate expectations is profound. Voyager has transcended its initial purpose, transforming from a mere scientific instrument into a symbol of human perseverance, a silent witness to the passage of time and the boundless reach of our curiosity. It's no longer just about the data. It's about the very act of enduring, of continuing to explore, long after anyone thought possible. Within 4 short years of their launch, the Voyagers had already completed all of their initial objectives. They had danced with Jupiter, marveling at its stormy countenance and its vibrant moons, and then gracefully waltzed with Saturn, revealing its intricate rings and the icy secrets of its satellites. Their mission, by all accounts, should have ended there. But the universe, it seems, had more plans for these quiet wanderers, and so did the forward-thinking minds at NASA. The mission, far from concluding, was extended given a new grander purpose. It was decided that these resilient little craft would be sent even further to include the 2 outer gas giants, Uranus and Neptune. This extension wasn't just a simple continuation. It was a testament to their robust design, a whisper of confidence in their enduring spirit. And then, with the successful completion of these extended planetary flybys, the ambition swelled even further. The stage was set for the even more audacious Voyager interstellar mission. The very name itself breathes wonder: interstellar, beyond the stars. The purpose now stretched beyond the known boundaries of our sun's familiar kingdom, seeking to explore the outer limits of the sun's sphere of influence, and thrillingly beyond. This wasn't merely about observing planets anymore. It was about charting the invisible frontiers of our solar neighborhood, pushing the very edge of our cosmic map. To grasp the magnitude of their journey, consider this Voyager 1 has now traveled an astonishing 22 billion kilometers from Earth. And its twin Voyager 2 follows closely behind at 18 billion kilometers. These are distances so vast, they humble the mind, making our terrestrial lives seem like a fleeting breath on a tiny speck of dust. If we were to try and visualize such distances, it would be like trying to trace a single, almost invisible thread, stretching from one side of a vast unlit cavern to another, with us standing at one end, peering into the endless dark. These silent, distant messengers have journeyed so far that they have, in fact, left the heliosphere, that protective bubble of solar wind and magnetic fields that cradles our solar system, and have now entered what we call interstellar space. They are literally floating in the space between the stars, a cold, vast emptiness where the sun's warmth and light are but a distant, faded memory. But even for these remarkably long-lived Voyager probes, time, that relentless current, is slowly, inevitably running out. The gentle hum of their power, generated by their radioisotope thermoelectric generators, is gradually diminishing. Perhaps as soon as 2025, a mere whisper of years from now, these incredible probes will finally lose their remaining power supply and, like distant stars winking out, go dark forever. This thought carries a certain poignant beauty, doesn't it? Like watching a beloved elder slowly, peacefully drift off to sleep after a life well lived. In preparation for this inevitable twilight, NASA has already begun the somber task of taking the probe's instruments offline one by one, like gently turning off the lights in a beloved home before leaving. This is done with the quiet hope of extending the life of the mission for just a few more precious years to gather every last fragment of data from their astonishing journey. Yet when the Voyager probes inevitably fall silent, they will not disappear without a trace. Oh no, they will leave behind a legacy so immense, so profound, that its value is truly unprecedented in its size and scope. The sheer volume of data, the intimate whispers from the edge of the known universe will continue to resonate through scientific halls for generations. It's a treasure trove of cosmic knowledge, a gift from the far reaches of space, patiently collected over decades. And so, as we enter the final days, the quiet twilight of the Voyager mission's active life, a powerful question emerges, one that whispers to our very souls. What exactly did Voyager 1 and 2 discover out there in the quiet, mysterious expanse? Did these probes and their delicate instruments truly hold up under the relentless rigors of interstellar travel, a journey they were never originally designed to undertake? And why, perhaps most intriguingly, are scientists so incredibly surprised by what they learned? These are the questions we will gently explore tonight allowing them to settle in our minds like soft stardust. Imagine for a moment the profound stillness of interstellar space, a canvas so vast that human imagination strains to comprehend it. And on that canvas, two tiny brushstrokes, two enduring whispers from humanity, continue their silent, relentless journey. The very fact that we can even ask these questions that we have, these faint echoes from so far away, is a miracle in itself. We will relive the remarkable journey these probes took after they left Neptune's orbit, traveling from the solar system's icy outer giants to the very brink of interstellar space. Their story is not just one of scientific triumph, but of enduring human curiosity, of dreams cast into the void, hoping to catch a glimpse of the universe's deeper truths. While Voyager 1 and 2 were originally meant to embark on a relatively brief 5-year mission, their enduring legacy, their remarkable longevity, is not simply a stroke of luck. It's a testament to the foresight, the quiet ingenuity, and the deep, almost poetic understanding of the cosmos held by their team of forward-thinking scientists and engineers. They made a number of design choices, subtle yet profound, that enabled these probes to hold up over a much, much longer journey than anyone could have initially dared to dream. These choices were not about brute force, but about elegance, about resilience, about a deep respect for the unforgiving nature of the void. Let's now drift a little deeper into the quiet wisdom that allowed the Voyager probes to defy their predicted lifespans and embark on a journey that stretched far beyond their initial blueprint. The enduring success of these little metallic messengers isn't a mere accident. It's a testament to the foresight of those who crafted them, the unsung heroes who thought not just for 5 years, but for decades, for a silent, enduring whisper across the cosmos. Imagine a team of gentle dreamers, scientists, and engineers who understood that in the vast, unforgiving emptiness of space, simplicity and redundancy would be their greatest allies. Their choices were not about flash and immediate glory, but about the quiet strength of lasting design, a deep, almost intuitive understanding of cosmic endurance. At the very heart of each Voyager probe, providing the gentle, unwavering pulse of life, lies a marvel of engineering, the radioisotope thermoelectric generator, or RTG. Think of it not as a roaring engine, but as a slow-burning, almost eternal candle, quietly flickering in the vast darkness. This isn't a power source fueled by chemical reactions or solar panels dependent on fleeting sunlight. Instead, the RTG converts the heat generated by the natural predictable decay of a radioactive isotope, plutonium-238, directly into electrical power. It's a process of quiet transformation, a soft, persistent hum of energy derived from the very fabric of matter decaying over time. Envision a tiny contained furnace radiating warmth, and that warmth in turn is gently coaxed into a steady flow of electricity enough to power the delicate instruments and communication systems that keep Voyager alive and talking across billions of miles. This elegant solution meant that Voyager was not tethered to the sun's fading light as it ventured further and further into the deepening twilight of the outer solar system. It carried its own gentle warmth, its own source of light and life within its very core, like a tiny star cradled in its metallic shell. This constant, unblinking flow of power is the silent heartbeat that has sustained these probes for nearly half a century, a testament to the graceful efficiency of radioactive decay. But even the most reliable heart needs safeguards. The engineers behind Voyager understood that the vastness of space is not just beautiful, it is also profoundly unforgiving. Failures, whether from micrometeoroid impacts, unexpected temperature fluctuations, or simply the slow wear and tear of cosmic radiation, were not just possibilities, they were certainties over such immense timescales. And so, woven into the very fabric of Voyager's design was a philosophy of redundancy. Imagine building a ship with not just one sail, but many and spare masts tucked away ready for any storm that might arise in the endless sea. Voyager was equipped with 11 scientific instruments, each designed to taste the cosmic winds, to listen to the whispers of distant worlds, to measure the subtle magnetic fields. And crucially, most of these instruments had built-in backups. If one sensor failed, another could step in quietly, taking its place, ensuring the continuous flow of precious data. It was a strategy born of deep respect for the unknown, an acknowledgement that even with the best planning, the universe holds its own surprises. Beyond the instruments, the very movement of the probes was safeguarded. To gently adjust their course to fine-tune their trajectory, they relied on 16 hydrazine thrusters. These small, precise jets, like tiny controlled breaths, allowed the probes to subtly alter their paths. And here again, the wisdom of redundancy shines through. 8 of these thrusters were backups. This meant that even if half of their delicate maneuvering systems failed, Voyager could still gently steer itself still. Follow the celestial highway laid out for it. It was a quiet reassurance built into every fiber of their being, a promise that they would keep going even when parts of them grew tired or succumbed to the cosmic elements. This meticulous approach to design this gentle layering of safety nets transformed the Voyager probes from mere machines into resilient explorers capable of adapting and enduring in the face of unimaginable challenges. Yet beyond the brilliance of their internal design, there was another crucial factor, a stroke of cosmic serendipity that elevated the Voyager mission from a brilliant endeavor to an unprecedented epic. The very moment of their launch in 1977 was not merely chosen by human schedule. It was blessed by the universe itself. NASA took advantage of a truly rare, almost mystical cosmic alignment, a once-in-176-year alignment of the planets. Imagine the planets of our outer solar system, Jupiter, Saturn, Uranus, and Neptune lining up in a celestial dance, a grand cosmic waltz that occurs only once every few human lifetimes. This wasn't just a convenient arrangement. It was a cosmic slingshot, a perfect celestial pathway waiting to be exploited. This extraordinary alignment offered 2 profound advantages. Firstly, it allowed for flybys of Neptune and Uranus with minimal course adjustments. Picture a ship sailing the open ocean where the winds are perfectly aligned, allowing it to glide effortlessly from one port to the next without needing to constantly trim its sails. Similarly, the planets were positioned in such a way that Voyager could simply drift from one to the next, requiring only tiny, precise nudges to stay on course. This conserved precious fuel that would be needed for the longer interstellar journey ahead. Every drop of hydrazine saved was another mile gained, another year of life extended. Secondly, and perhaps most ingeniously, this alignment gave the probes a gravity assist from each of the giants they visited. This concept, revolutionary at the time, is like a cosmic handoff, a gentle push from a colossal friend. Imagine a child on a swing. If you give them a push at just the right moment in their arc, they swing higher and faster, gaining momentum without expending their own energy. In the same way as each Voyager probe gracefully approached a massive planet like Jupiter or Saturn, it was gently pulled by the planet's immense gravitational field, slingshotting around it. This maneuver didn't just bend the probe's path. It transferred a tiny fraction of the planet's immense orbital energy to the spacecraft, thereby increasing their effective velocity beyond what they could get from their own rocket propulsion. It was an act of cosmic judo, transforming the raw power of a rocket launch into elegant, sustainable momentum, pushing the probes faster and further with each planetary encounter. This idea of a gravity assist, though seemingly simple, was relatively new at the time. It had only been attempted previously on NASA's Pioneer missions to Jupiter and Saturn, which served as quiet predecessors, whispering the possibilities. Voyager refined this technique, turning it into a ballet of celestial mechanics, a masterclass in cosmic efficiency. Each flyby was not just an observational opportunity, it was a deliberate acceleration, a boost into the next leg of their incredible journey. Without these precise gravitational slingshots, the Voyagers would have needed far more fuel. far more time, or perhaps would never have reached the distances they have today. Their current speed, carrying them ever deeper into the interstellar void, is a direct legacy of this celestial dance, a testament to the elegant physics that underpins the universe. The planets themselves, through their silent gravitational pull, became partners in this grand exploration, lending their immense power to humanity's small emissaries. It was a symphony of engineering and celestial alignment, a perfectly timed cosmic whisper that set these probes on a trajectory toward eternity. The meticulous planning, the strategic use of every available resource, whether it was the slow, steady hum of the RTG, the foresight of redundant systems, or the once-in-a-lifetime cosmic alignment, all converged to create something truly exceptional. These weren't just rockets and probes. They were carefully choreographed ballets of science and opportunity, designed to push the boundaries of what was thought possible. The brilliance lay not just in building them, but in understanding the delicate interplay of physics and celestial mechanics, allowing these quiet explorers to ride the waves of gravity and time into the unknown. Each choice, each design detail was a subtle nod to the future, a quiet hope that these machines would not only achieve their immediate goals, but would endure, becoming persistent witnesses to the vastness and mystery of the universe. Their longevity is a testament to this profound foresight, an enduring monument to human ingenuity and the boundless potential when we work in harmony with the cosmos. Now let us gently follow our quiet companions as they began to truly stretch their wings, leaving behind the familiar plane of our planetary neighborhood. Imagine our solar system as a vast flat disk, almost like a thin cosmic dinner plate. Most of the planets, including our own Earth, orbit the Sun roughly within this flat plane, which we call the ecliptic. It's our familiar celestial highway, the well-trodden path of planetary travel. But the Voyager probes, with their extended mission, were destined for paths less traveled, for journeys that would take them not just further out, but also up and down into the three-dimensional grandeur of space. In 1981, after its graceful dance with Saturn, Voyager 1 performed a subtle yet profoundly significant maneuver. It gently curved its path, escaping the ecliptic, that comfortable orbital plane. Think of it like a leaf, caught in a swirling stream, suddenly being lifted by a gentle breeze, floating upwards and away from the surface of the water. Voyager 1 headed a remarkable 35 degrees to the north of this familiar plane. This wasn't just a deviation, it was a deliberate choice, a gentle but firm departure from the well-worn paths. This upward trajectory allowed it to begin its long solitary journey towards the edge of the heliosphere, looking back at our solar system from a new elevated perspective, an angle from which no human-made object had ever gazed before. Its twin Voyager 2 would later embark on its own mirrored dance, though in a different direction. After its encounters with Uranus and Neptune, Voyager 2 went under the ecliptic heading 48 degrees to the south. Picture it as a mirrored flight, two explorers charting different vertical dimensions of our solar system, one ascending above the other, descending below. This divergence in their paths was not accidental. It was a brilliant strategic choice. By traveling on these distinct trajectories, one veering north, the other dipping south, the probes would eventually be able to provide us with a much broader, more comprehensive understanding of the heliosphere, that vast magnetic bubble carved out by our sun's influence. They would be tasting the solar wind and magnetic fields from entirely different cosmic perspectives, painting a richer, more detailed picture of our sun's domain. It's as if we sent two scouts to explore a vast invisible shield, each approaching from a different angle to map its unseen contours. As the Voyager planetary mission gracefully transitioned into the more ambitious Voyager interstellar mission, a poignant decision had to be made. To conserve the precious dwindling power from their gentle RTGs, that quiet internal hum we discussed earlier, a difficult but necessary sacrifice was required. The cameras on both probes were deactivated. Imagine an explorer, deep in an uncharted wilderness, realizing they must lighten their load to survive the longest leg of their journey. They might choose to leave behind their sketching tools, knowing that the most important part now is simply to be there to transmit the essential data, even if the visual story cannot be told directly. This moment in the Voyager story is immortalized by one particular image, a photograph that has woven itself into the fabric of human consciousness, the famous pale blue dot. This was the very last image taken by Voyager 1, captured from a staggering distance of around 6 billion kilometers from Earth. Allow that number to settle in your mind for a moment. 6 billion kilometers. From that incredible vantage point, our vibrant living Earth appears as nothing more than a tiny, almost invisible speck, a solitary, fragile pixel suspended in a vast, indifferent sunbeam. It is to this day the most remote image of Earth ever taken. The pale blue dot is more than just a photograph. It is a profound philosophical statement, a mirror held up to humanity. When you gaze upon that image, you can't help but feel a deep sense of humility, a profound recognition of our smallness in the face of cosmic immensity. All of human history, every joy and sorrow, every empire built and fallen, every love story, every scientific discovery, every war, every moment of peace, all of it transpired on that tiny, faint blue dot. It reminds us of our shared fragility, our interconnectedness on this precious lone island in the universe. It whispers to us of the futility of our divisions and the paramount importance of cherishing this one home we collectively share. The decision to turn off the cameras while pragmatic imbued this final photograph with an almost sacred significance. It was the last visual farewell, a silent promise to keep going, to seek out truths that no camera could capture, truths about the very fabric of interstellar space. However, this poignant visual farewell was barely the beginning of the Voyager's true journeys into the unknown. To reach interstellar space, that vast sea between the stars, the probes would first have to traverse a series of invisible, yet incredibly dynamic cosmic boundaries, like passing through distinct swirling currents in a vast ocean. These aren't solid walls or visible lines. They are regions defined by the interplay of subtle energies and invisible forces shaped by the breath of our sun and the whispers of the galaxy beyond. The first of these ethereal thresholds is known as the termination shock. Imagine a river flowing swiftly and smoothly for a long distance, but then suddenly encountering a formidable barrier, perhaps a hidden, unyielding wall of water. The smooth flow is disrupted, becoming turbulent and chaotic. In a similar cosmic fashion, the termination shock is a region where the hypersonic solar winds, a steady supersonic stream of charged particles constantly emanating from our sun, encounter fierce, unyielding resistance from the interstellar wind. Think of it as a cosmic breaking point where the sun's powerful exhalation slams into the thin but persistent breath of the galaxy itself. Here, the solar wind, which has been screaming outwards for billions of miles, abruptly slows down, creating a region of turbulent heated plasma. It's an invisible cosmic waterfall where the energy of our sun's outflow dramatically changes its character. Beyond the termination shock, the Voyagers would then encounter a sprawling turbulent region called the heliosheath. Imagine the water that has just gone over our cosmic waterfall. It doesn't immediately become calm. Instead, it forms a vast swirling eddy, a turbulent zone where the now slowing solar winds pile up, becoming denser and hotter. This region acts like a vast bubbly buffer, a cosmic mudroom or an antechamber between the sun's immediate dominion and the greater galaxy. In the heliosheath, the solar wind, no longer supersonic, is slowed, compressed, and warmed by its collision with the interstellar medium. It's a dynamic, churning environment, a cosmic mixing bowl where the sun's influence begins to mingle with the whispers from beyond. For millions of miles, the Voyagers would drift through this agitated region, experiencing the complex interplay of forces that define our solar system's true outer atmosphere. It's a place of transition where the sun's powerful breath slowly dissipates before meeting the vastness of interstellar space. Finally, at the very edge of this cosmic bubble lies the heliopause. This is the ultimate final boundary, the delicate membrane that separates our heliosphere, the vast region of space dominated by our sun's solar wind and magnetic field, from the true, boundless expanse of interstellar space. Think of it as the very edge of a warm, comforting bubble meeting the vast, cold ocean beyond. It is the place where the outward push of the solar wind finally loses its battle against the inward pressure of the interstellar medium. It's not a solid wall, but a dynamic fluctuating boundary, a point of equilibrium where the two great cosmic currents finally balance each other out. Crossing the heliopause is not just entering a new region of space. It's entering a new realm of physics, a realm dominated not by our familiar sun, but by the subtle energies and distant influences of the galaxy itself. However, in spite of what you may instinctively think, the start of the interstellar medium doesn't actually mark the official end of our solar system. This is where our understanding of solar system expands to truly breathtaking scales. Indeed, it will be another 300 years until Voyager 1 even reaches the Oort cloud. Imagine the Oort cloud as a vast ethereal shell, a colossal sphere of billions of icy planetesimals, comets and debris surrounding our solar system, like an enormous fragile bubble. It's the true outermost frontier of our sun's gravitational influence, a dormant reservoir of icy wanderers, stretching for light years in every direction. Our current maps of the solar system, which often end at Neptune, are merely sketches of a tiny inner courtyard. The Oort cloud is the sprawling, dimly lit estate beyond the Garden Gate, and the journey doesn't end there. Even after passing through the Oort cloud, Voyager will still be within our sun's gravitational dominion. However faint that pull might be, it will be another astonishing 30,000 years until it finally exits this vast cloud, leaving our solar system forever. 30,000 years. That is a timescale that dwarfs human civilization, that makes our entire recorded history seem like a mere blink. Picture a tiny forgotten pebble tossed into an endless sea, slowly inexorably drifting further and further from the shore, until the very concept of the shore becomes a myth, a distant, faded memory. When that happens, Voyager 1 will truly be an interstellar traveler adrift in the vast ocean of our Milky Way galaxy, a silent, enduring testament to the human spirit's insatiable quest for the unknown. This journey far beyond our current comprehension is a testament to the enduring nature of the cosmos itself and the humble, persistent machines we send to whisper back its secrets. Let us now shift our gaze back to those vast invisible boundaries that the Voyager probes had to patiently traverse, those subtle shifts in the cosmic currents that marked their passage from our sun's immediate domain into the grander, more mysterious realm beyond. These aren't borders drawn on a map with sharp defined lines. Instead, they are dynamic fluid regions like currents and eddies in an enormous invisible ocean, each one marking a profound change in the very fabric of space and the energies that flow through it. To truly appreciate the Voyager's journey, we must first understand the nature of these cosmic thresholds, these whispered transitions that separate the familiar from the truly unknown. Imagine our sun not just as a source of light and warmth, but as a colossal breathing entity, constantly exhaling a powerful invisible breath known as the solar wind. This wind is a steady supersonic stream of charged particles, electrons, protons, and alpha particles, constantly streaming outwards from the sun's scorching outer layer. It inflates a gigantic bubble around our solar system, a protective shield called the heliosphere that pushes against the interstellar medium, the thin gas and dust that fills the space between stars. Think of it as our sun's personal territory, its vast magnetic bubble in the galactic ocean. The first significant boundary the Voyagers encountered on their long outward journey was the termination shock. Picture a mighty river flowing smoothly and swiftly, but then suddenly it meets a vast, unyielding wall of opposing water. The river doesn't stop, But its character changes dramatically. It becomes turbulent, chaotic, and loud. In the cosmos, this is precisely what happens at the termination shock. The hypersonic solar winds, which have been screaming outwards at incredible speeds for billions of kilometers, suddenly run into fierce, unyielding resistance. This resistance comes from the interstellar wind, the incredibly sparse but persistent flow of particles from outside our solar system, pushing inwards. At the termination shock, the solar wind, previously supersonic, slams into this interstellar pressure, creating a colossal shock wave. It's not an explosion, but a sudden dramatic deceleration. The solar wind slows down from supersonic speeds to subsonic speeds, much like a jet plane hitting a wall of thick air. This violent collision doesn't just slow the particles, it also heats them up intensely. So the termination shock is a region of immense turbulence, a cosmic whitewater rapids, where the energy of our sun's outflow is converted into heat and agitation. For the Voyager probes passing through this region was like sailing into a storm, feeling the invisible buffet of cosmic forces as the very nature of the solar wind around them dramatically changed. Their instruments would have registered the sudden increase in density, the heightened temperature, and the swirling chaos of the magnetic fields, a clear signal that they were no longer in the familiar steady flow of the inner heliosphere. This was the first true taste of the cosmic frontier, a turbulent welcoming committee to the outer reaches of our sun's influence. Beyond the termination shock, where the solar wind has now slowed and become more agitated, the Voyagers drifted into a vast, swirling region known as the heliosheath. Imagine the water that has just gone over our cosmic waterfall. It doesn't immediately become still. Instead, it forms a vast, turbulent, and swirling eddy, a cosmic antechamber where the now slowed solar winds pile up. Here, these particles become denser and hotter as they are compressed and stirred by the interaction with the interstellar medium. Think of the heliosheath as a gigantic cosmic buffer zone, a turbulent mixing chamber that separates the fast-flowing solar wind of the inner heliosphere from the cold, still waters of truly interstellar space. It's a place of transition where the sun's influence still reigns, but it's a tired, compressed, and turbulent reign, constantly being pushed back by the unseen forces from beyond. Within the heliosheath, the magnetic fields carried by the solar wind become tangled and complex like threads of wool caught in a strong current. The particles here are heated not by the sun's direct rays, but by the very act of compression and turbulence. It's a dynamic, churning environment, a place where the lingering breath of our sun prepares to meet its end. The Voyagers spent many years traversing this immense region, patiently gathering data on its fluctuating temperatures, densities, and magnetic configurations. Each signal sent back across the billions of miles was a precious data point, helping us to gradually construct a clearer picture of this mysterious zone, a place that was largely theoretical before the Voyagers provided us with direct observations. It's in the heliosheath that the sun's outward dominion truly begins to fray at the edges, where its power starts to yield to the subtle, pervasive influence of the wider galaxy. Finally, after journeying through the chaotic embrace of the heliosheath, the Voyagers would reach the ultimate final boundary of our sun's personal realm, the heliopause. Picture it as the very edge of a warm, comforting bubble, thin and ethereal, meeting the vast, cold and true ocean of interstellar space. This is the critical threshold where the outward push of the solar wind, after being slowed and compressed in the heliosheath, finally balances and then is overcome by the inward pressure of the interstellar medium. It's the point of equilibrium where the two great cosmic currents, one emanating from our sun and the other flowing through the galaxy, finally push against each other and reach a standstill. The heliopause is not a solid wall, nor is it a perfectly smooth, clear-cut line. Instead, it's a dynamic, fluctuating boundary, a sort of energetic membrane. On one side, you have the remnants of our sun's energetic exhalation. On the other, the pristine alien particles and magnetic fields of the galaxy itself. For decades, scientists could only speculate about the exact location and nature of this boundary. Some early models based purely on theoretical calculations placed it as close as Jupiter's orbit, suggesting our solar bubble was far smaller than imagined. Others pushed it much, much further out. The precise distance remained a profound mystery, a fundamental question about the true size and reach of our sun's domain. The Voyagers were sent in part to resolve this very question, to be our gentle silent probes feeling out the edge of our cosmic home. It's crucial to understand what distinguishes the solar wind from the interstellar medium. The solar wind, as we've discussed, is a steady stream of charged particles, electrons, protons, and alpha particles that originate from the sun's fiery outer layer, its corona. It's our sun's breath carrying its magnetic field and energy outwards. The interstellar medium, by contrast, is a vastly different beast. It consists of charged particles, gases primarily hydrogen and helium, and tiny specks of cosmic dust. This material isn't from our sun. It's the leftover debris and raw ingredients from the Big Bang itself, the fundamental matter that constitutes the space between stars. It also includes heavier elements forged in ancient supernovae, the colossal explosions of dying stars that enriched the galaxy with new elements. When these two streams, the solar wind and the interstellar medium, hit each other at the heliopause, they don't just stop. They change course. They form this region of delicate equilibrium, a boundary where the pressures from inside and outside our solar bubble are finally balanced. It's like the crashing of two powerful bodies of water against each other, where the energy dissipates and a new, relatively still zone is created between them. The significance of crossing this heliopause cannot be overstated. It means moving from a region where our sun's magnetic field and particles are dominant to a region where the magnetic fields and cosmic rays of other stars and the galaxy as a whole begin to take precedence. It's the true gateway to the wider cosmos, a step into the realm of our galactic neighbors. But in spite of what you may think, the start of the interstellar medium doesn't actually mark the official end of our solar system as a whole. This is where our understanding of solar system expands to truly breathtaking, almost unfathomable scales. Indeed, even after crossing the heliopause, the Voyagers are still gravitationally speaking tethered to our sun. They are still within its profound, though now incredibly faint, gravitational grasp. It will be another astonishing 300 years until Voyager 1 even reaches the Oort cloud. Imagine the Oort cloud as a vast ethereal shell, a colossal sphere of billions of icy planetesimals, comets, and cosmic debris surrounding our solar system, like an enormous, fragile, and incredibly diffuse bubble. It's the true outermost frontier of our sun's gravitational influence, a dormant reservoir of icy wanderers, stretching for light years in every direction. Our current mental maps of the solar system, which often conclude abruptly at Neptune or Pluto, are merely sketches of a tiny familiar inner courtyard. The Oort cloud is the sprawling, dimly lit estate beyond the Garden Gate, a region of profound stillness and unimaginable distance. It is here that the sun's gravitational whisper is still strong enough to hold onto these distant icy bodies, preventing them from drifting away into the interstellar void. And the journey doesn't end even after traversing the Oort cloud. Even after passing through this vast icy halo, Voyager 1 will still be, however faintly, under our sun's gravitational dominion. It will be another astonishing 30,000 years until it finally exits this colossal cloud, truly leaving our solar system forever. 30,000 years. That is a time frame that dwarfs human civilization, that makes our entire recorded history seem like a mere blink. Picture a tiny forgotten pebble tossed into an endless sea, slowly, inexorably drifting further and further from the shore, until the very concept of the shore becomes a myth, a distant, faded memory. When that happens, when Voyager 1 finally passes beyond the gravitational pull of our sun, it will truly be an interstellar traveler. adrift in the vast, star-filled ocean of our Milky Way galaxy, a silent, enduring testament to the human spirit's insatiable quest for the unknown. This journey far beyond our current comprehension is a testament to the enduring nature of the cosmos itself and the humble, persistent machines we send to whisper back its secrets, to chart the very edges of our cosmic home, and to hint at the profound, unexplored realms that lie beyond. Now let us gently glide into a region where the Voyagers made an incredible discovery, a finding so unexpected it compelled scientists to completely redraw their mental maps of our solar system's outer frontier. This region is the heliosheath, that vast, turbulent buffer zone we discussed, where the sun's breath has slowed and compressed after passing the termination shock. Before the Voyagers, our models of this area were mostly theoretical, elegant equations that predicted a relatively smooth and predictable transition. But the universe, as it so often does, proved to be far more intricate and beautiful than our neat assumptions. The sun, that magnificent star at the heart of our system, constantly emits a magnetic field. This field is not static. It spins outwards with the solar wind. And here's where things get interesting. Because the sun's magnetic field spins in opposite directions on its north and south poles, where these opposing forces meet, they create a kind of ripple. Imagine dropping a stone into a perfectly still pond. The rings spread outwards, ever widening. On a cosmic scale, the sun creates something similar, a vast undulating structure called the heliospheric current sheet. It's like a colossal wavy skirt of magnetic influence spiraling outwards from the sun's equator, carrying its magnetic polarity far into space. This sheet is incredibly thin, but stretches for billions of miles, a gentle invisible wave propagating through the solar system. However, when this massive rippling current sheet reaches the termination shock, that turbulent cosmic waterfall where the solar wind slams into interstellar pressure, something truly remarkable happens. The sheet compresses as though those gentle ripples were suddenly hitting the very edge of a colossal, unseen swimming pool. Instead of continuing to spread smoothly, the ripples begin to stack up, piling on top of each other. Think of it like ocean waves approaching a shallow shore. They grow taller and closer together before they break. This compression, this stacking of magnetic ripples, was the first hint of the strange dynamic environment Voyager was about to unveil. And here is the groundbreaking discovery that sent ripples of surprise through the scientific community. The Voyager probes discovered that after the termination shock, these stacked up ripples don't just stay stacked. Instead, they form what scientists now call magnetic bubbles. Picture them not as a smooth, continuous surface, but as a vast, fluctuating and effervescent expanse, like champagne bubbles rising in a giant invisible glass. These aren't solid bubbles, but pockets of magnetic field lines that have become disconnected from the sun, pinching off and forming isolated magnetic islands within the heliosheath. Imagine our solar system's protective bubble not as a perfectly inflated balloon, but as one with tiny, restless effervescences, forming and dissipating at its edges, a ceaseless, almost whimsical dance of magnetic energy. This finding completely changed our understanding. Before Voyager, scientists largely envisioned the boundary of the heliosheath as a relatively smooth and clear-cut region, a predictable transition zone. But the reality, as revealed by the brave little probes, was far more complex, far more dynamic. The heliosheath, it turns out, is a fluctuating and magnetically bubbly environment. It's a turbulent, frothy expanse, constantly roiling and churning with these ephemeral magnetic bubbles. This messy finding, as some scientists affectionately called it, wasn't a problem. It was an invitation. It prompted a complete and humble revision of our long-held models of the heliosheath. This is a beautiful example of the scientific process in action. Theoretical models born from brilliant minds and elegant equations are always subject to the scrutiny of direct observation. And sometimes the universe whispers back a truth far stranger, far more nuanced than we ever dared to imagine. The Voyagers, in their quiet persistence, showed us that the very edge of our sun's influence is not a serene, ordered frontier, but a lively, chaotic, and effervescent boundary brimming with unseen magnetic activity. It's a reminder that even in the vast emptiness of space, there is an incredible, almost artistic complexity waiting to be discovered, if only we have the courage and the patience to send our messengers out to listen. Let's dwell for a moment on the profound implications of these magnetic bubbles. What does it mean for the heliosheath to be bubbly? Imagine the sun's magnetic field lines, usually extending outward like long, invisible threads. As these lines reach the termination shock and the subsequent heliosheath, they become compressed and tangled due to the interaction with the interstellar medium. The solar wind, though slowed, still carries a magnetic field with it. When this slowed, wind meets the pressure from outside, the magnetic field lines can reconnect with themselves in unexpected ways. Think of a long piece of string. If you pull both ends, it's straight. But if you push the ends together, it can buckle and loop. When these loops get tight enough, they can pinch off, forming closed-off magnetic structures. The bubbles. These aren't empty bubbles. They're pockets of trapped solar wind plasma and magnetic field that have become temporarily isolated from the main flow of the sun's influence. They form and dissipate constantly, changing the magnetic landscape of the heliosheath. The discovery of these ephemeral structures means that the boundary of the heliosheath is not a sharp, well-defined line like a drawn circle. Instead, it's fuzzy, dynamic, and constantly reorganizing itself. It's like the edge of a foam, where bubbles are always popping and new ones are forming, creating a perpetually shifting frontier. This understanding is critical because the heliosheath acts as our solar system's first line of defense against the more energetic particles from deep space, known as galactic cosmic rays. These high-energy particles, originating from supernovae and other violent events across the galaxy, can be harmful to spacecraft and potentially future human explorers. How effectively the heliosheath deflects or traps these cosmic rays depends on its structure. If it's a calm, smooth boundary, it might behave one way. But if it's a turbulent, bubbly, magnetically tangled mess, its protective capabilities might be very different. The Voyager's discovery suggests that our shield is far more complex and perhaps even more effective in some ways than we previously thought, acting as a kind of constantly churning magnetic filter. The sheer surprise among scientists upon learning about these magnetic bubbles was palpable. For decades, our theoretical models built on elegant mathematical principles had painted a picture of a largely uniform and predictable heliosheath. These models, while powerful, relied on certain assumptions about the behavior of plasma and magnetic fields in such extreme conditions. Voyager's direct measurements, however, were like a gentle hand drawing back a curtain, revealing a hidden, vibrant reality. It forced a moment of humble recalibration for the scientific community. It wasn't about the models being wrong in a simplistic sense, but rather incomplete. They were approximations that needed the raw, unvarnished truth from the universe itself to be refined and deepened. This is the beauty of exploration, isn't it? We send out our small, brave vessels not just to confirm what we already suspect, but to challenge our very assumptions, to ask the cosmos to show us something entirely new. The magnetic bubbles are a testament to this, a quiet revelation that the universe is always ready to surprise us, always ready to nudge our understanding forward in unexpected directions. It's a reminder that even in the most fundamental aspects of our cosmic neighborhood, there remain profound mysteries waiting for a patient observer to uncover them. The implications of these bubbles stretch further still. They suggest that the magnetic interaction between our sun's outflow and the interstellar medium is far more intricate than simple compression. It implies a dynamic dance of reconnection and fragmentation where magnetic field lines are constantly breaking and reforming. This kind of complex magnetic topology can influence how particles move through the heliosheath, how cosmic rays are scattered, and ultimately, how our solar system interacts with the wider galactic environment. It's a subtle, yet profound discovery that impacts our understanding of space weather, not just within our solar system, but at its very edges. The fact that these observations came from probes built over 40 years ago, operating on technology designed for a fraction of their current lifespan, only adds to the wonder. Imagine a vintage car meticulously maintained, not only still running, but discovering entirely new roads and landscapes far beyond its wildest dreams. The Voyagers are precisely that, old friends, quietly performing groundbreaking science from the very frontiers of our knowledge. Their instruments, though aging, are still capable of detecting these subtle fluctuations, these effervescent magnetic whispers, and sending them back across the cosmic gulf. This ongoing stream of data from the heliosheath, particularly about its bubbly nature, continues to inform and refine our sophisticated computer simulations. Scientists are now working to incorporate these new findings into their models, creating a more accurate and vibrant picture of our solar system's true extent and its interaction with the interstellar medium. It's a continuous feedback loop between the quiet, persistent observation from afar and the diligent, imaginative work back on Earth. The Voyagers, in their gentle journey, have become our ultimate truth-tellers, challenging our preconceived notions and guiding us toward a more complete and infinitely more fascinating understanding of the cosmic ocean we inhabit. So as we contemplate these magnetic bubbles, this effervescent edge of our solar bubble, let us marvel not only at the scientific discovery itself, but at the beautiful humility it demands from us. It reminds us that our maps of the universe are always works in progress, always open to revision, always waiting for the next whisper from the void to add another layer of detail, another unexpected splash of color. And in that constant state of learning and relearning lies the true joy and endless wonder of scientific exploration. The Voyagers are not just sending back data, they are sending back a profound lesson in open-mindedness, a gentle reminder that the universe holds endless surprises for those patient enough to listen. Let us now trace the path of our first intrepid explorer, Voyager 1, as it approached the ultimate frontier, the very edge of our sun's dominion, and made history in a quiet, almost imperceptible way. For years, it had traversed the turbulent heliosheath, sampling its densities and temperatures, listening to the hum of those magnetic bubbles we just explored. But then, on a day that would forever be etched into the annals of space exploration, something profound occurred, marking a true, undeniable transition into the vastness beyond. It was the 25th of July, 2012. On this day, the Voyager 1 space probe became the first man-made object to truly leave the sun's heliosphere and enter interstellar space. Imagine a tiny, fragile ship that has sailed across a vast, swirling sea, finally reaching the open, limitless ocean beyond. This was not a dramatic explosion or a visible crossing. It was a subtle shift in the cosmic winds detected by the sensitive instruments on board, a change in the very feel of the space around it. The event itself, though monumental, was met with a scientific caution, a deep, almost reverent need for verification, before announcing such a profound shift in our cosmic address. At this point in its journey, Voyager 1 was traveling at an incredible speed, a silent, relentless momentum that carried it ever further from its home. It was moving at approximately 540 million kilometers per year, which, to put into perspective, is about 3.6 astronomical units AU per year. An astronomical unit, as a gentle reminder, is the average distance between Earth and the Sun, a cosmic measuring stick. So every year, Voyager 1 was adding more than 3.5 times the Earth-Sun distance to its journey, a testament to the powerful gravity assists it received from the outer planets so long ago. This speed, this enduring velocity, was crucial for it to reach the distant heliopause within a human timescale. Without that cosmic slingshot, its journey would have been far longer, perhaps impossible, within the lifespan of its power source. The distance at which Voyager 1 crossed the heliopause was approximately 120 astronomical units from the Sun. This number itself was a profound revelation, a quiet whisper that reshaped our understanding of our solar system's true size? For decades, scientists had theorized about where exactly the heliopause occurred. These early models were based on our best understanding of solar wind pressure and interstellar medium density, but without direct measurements, they were simply educated guesses. Funnily enough, some early models, conservative in their estimates, put the heliopause as close as Jupiter's orbit, suggesting our protective solar bubble was much smaller and more vulnerable than we thought. Others, more optimistic, pushed it much further out. Voyager 1, like a silent, honest cartographer, finally provided the definitive answer, extending our cosmic map far beyond what many had imagined. It was like finding the edge of a vast, mysterious forest, much further than anticipated, revealing a larger, more expansive domain than previously mapped. This precise measurement underscored the invaluable role of direct observation in refining our theoretical understanding of the cosmos. Remember, the heliopause, that crucial boundary we discussed earlier, is where the sun's solar wind, its powerful outflow of charged particles, is finally stopped by its collision with the interstellar medium. Picture it as the dramatic crashing of two powerful bodies of water against each other, where their opposing forces create a dynamic yet balanced interface. On one side, you have the solar wind, that steady stream of charged particles, electrons, protons, and alpha particles, constantly emanating from the sun's outer layer, its corona. This is our sun's constant breath filling the heliosphere. On the other side, you have the interstellar medium, a vastly different cosmic broth. It consists of charged particles, diffuse gases, primarily hydrogen and helium, the raw ingredients of the universe, and tiny specks of cosmic dust, all remnants from the Big Bang and the explosive deaths of ancient supernovae that enriched the galaxy. When these two distinct streams, one from our sun and one from the vast galaxy, collide, they don't simply vanish. Instead, their opposing pressures cause them to change course, to deflect each other, and to form a region of delicate equilibrium. That is the heliopause boundary. It's a cosmic standoff, a silent balance of colossal forces. At first, even with the data streaming back, NASA scientists weren't entirely sure if Voyager 1 had truly crossed the heliopause and entered into interstellar space. The stakes were incredibly high. This was an unprecedented moment in human history, and absolute certainty was paramount. Their cautious nature is a hallmark of true scientific inquiry. What they saw was compelling, but also puzzling. The probe's plasma wave detector, an instrument that essentially listens to the vibrations and oscillations in the charged particles around the spacecraft, found a massive increase in plasma density. It registered an astonishing 80 times what it had detected in the outer heliosheath, a clear sign that it had entered a new, denser medium. Along with this, there was a noticeable spike in galactic cosmic rays, those high-energy particles from beyond our solar system, which the heliosphere usually deflects. A sudden surge in these particles indicated that the protective bubble of our sun was no longer acting as a shield, suggesting it was indeed outside. These two pieces of evidence, the dramatic increase in plasma density and the spike in galactic cosmic rays, were strong indicators that Voyager 1 had left the heliosphere. They were like finding footprints of a different creature in a new land. But then, something truly strange happened, or rather didn't happen, that left scientists baffled and filled with a profound sense of cosmic mystery. After crossing the heliopause, Voyager 1 detected no change in the ambient magnetic field. Absolutely none. Why was this so surprising? Why did this absence of change cause such a stir? Well, our theoretical models, the sophisticated mathematical constructs we had built to understand this frontier, largely assumed that in a region truly dominated by the magnetic fields of other stars and the wider galaxy, the ambient magnetic orientation would change. We expected a shift, a new alignment, a different magnetic fingerprint from the galactic medium compared to our sun's own magnetic field. Imagine stepping from a room with a distinct flowing current of air into another where the air flows in a completely different direction. You would expect to feel that change, but Voyager 1 detected no discernible changes in the ambient magnetism, as if the air in the new room was still flowing exactly as it was in the old one. This lack of change was so unexpected, so contrary to prevailing models, that NASA was incredibly cautious. They waited nearly a year, meticulously analyzing the data, double-checking their instruments, and running countless simulations before finally announcing with confidence that Voyager 1 had, in fact, entered interstellar space. This period of intense scrutiny underscores the humility and rigor of science. It's not enough to see something new. You must be sure, absolutely sure, of what you are seeing, especially when it challenges long-held beliefs. The universe, it seems, held a subtle, magnetic secret, one that only direct observation could unveil, pushing our understanding of the interstellar medium into new, unexpected territory. The quiet strength of Voyager 1 had not only crossed a physical boundary, but had also challenged the very assumptions upon which our understanding of that boundary was built. Let us now turn our gentle gaze to Voyager 2, the twin explorer patiently following in its siblings' cosmic footsteps, yet destined to reveal its own unique set of surprises, as it too crossed into the interstellar void on the 5th of November 2018, a quiet but momentous day for humanity. Voyager 2 joined Voyager 1 in becoming the second man-made object to finally enter interstellar space. This was not just a repeat performance. It was a reaffirmation, a second witness to a truly historic moment, solidifying our understanding of where our sun's protective bubble truly ends. Voyager 2, though traveling at a slightly slower pace than its predecessor, maintained an impressive velocity testament to the enduring power of its initial gravitational assists. It was moving at approximately 490 million kilometers per year, or roughly 3.3 astronomical units per year. Imagine two very determined, very patient marathon runners, one slightly ahead of the other, both relentlessly pushing towards an unseen finish line far beyond the horizon. Its journey, like Voyager 1's, was a testament to the elegant efficiency of the gravity assist maneuver, harnessing the colossal power of the gas giants to propel it to speeds otherwise unattainable. Crucially, the crossing for Voyager 2 also occurred at approximately 120 astronomical units from the Sun. This precise distance, matching Voyager 1's crossing 6 years prior, was in itself a significant confirmation. It suggested a remarkable consistency in the heliopause's location, despite the passage of time and the dynamic nature of our Sun. It was as if two different ships sailing years apart had landed on the exact same remote shore, and mirroring Voyager 1's baffling observation. Voyager 2 detected no change in the ambient magnetic field as it crossed into interstellar space. This was a profound, almost unsettling consistency. The theoretical models which predicted a distinct shift in magnetic orientation upon entering a region dominated by galactic magnetic fields were once again challenged. The universe, it seemed, was whispering a repeated message, one that suggested our understanding of interstellar magnetism at this particular boundary needed a fundamental rethink. This repeated observation from two different probes, 6 years apart, lent immense weight to the finding, transforming it from an anomaly into a robust, undeniable truth. But then something else entirely surprised scientists, adding another layer to the cosmic enigma. You see, our Sun is not a perfectly constant, unchanging star. It goes through 11-year solar cycles periods, during which its activity, including solar flares, coronal mass ejections, and the strength of the solar wind, waxes and wanes. Imagine the Sun as a great cosmic heart, its pulse strengthening and weakening over a regular rhythm. When solar activity is high, the solar wind is more vigorous, theoretically pushing the heliopause further out, expanding the size of our protective bubble. Conversely, when solar activity is low, the heliosphere is expected to contract. Voyager 2's crossing of the heliopause occurred at a time when solar winds were peaking. Our models, based on the assumption that the size of the heliosphere would fluctuate with the solar cycle, predicted that it should have been expanding at this very moment. This meant that when Voyager 2 made its crossing, it was expected to find the heliopause much further away than where Voyager 1 had encountered it during a different phase of the solar cycle. Imagine a balloon that expands and contracts with each breath. If you measure its edge during a deep inhale, you'd expect it to be larger than during an exhale. Yet here was the profound surprise. Voyager 2 crossed the heliopause at exactly the same distance Voyager 1 had 6 years prior. This unexpected consistency completely defied the prevailing models. It was as if two measurements of our breathing cosmic balloon, taken at different points in its cycle, yielded the exact same size. This observation was a powerful, undeniable demonstration of the value of testing theoretical models with field data. No matter how elegant or logical a scientific model appears on paper, the ultimate arbiter of truth is direct observation, the unvarnished reality delivered by our intrepid explorers. The universe, in its quiet wisdom, was once again showing us that our assumptions, however well-reasoned, are only stepping stones to a deeper understanding. This finding, combined with the consistent magnetic field observation, has led scientists to a profound re-evaluation of the heliopause. We now suspect the boundary between the heliosphere and the interstellar medium is much more twisted, dynamic, and filled with fluctuations than prior models had proposed. It's not a smooth expanding and contracting bubble. It's a far more complex, perhaps even wrinkled and constantly shifting interface. Imagine a balloon that isn't just expanding and contracting, but also constantly rippling and folding in on itself, its surface, never truly smooth, always in motion. One leading idea, a captivating hypothesis, attempts to explain these perplexing observations. It suggests that our sun billions of years ago emerged from a hot and heavily ionized region, perhaps following the cataclysmic explosion of one or more supernovae. These ancient cosmic explosions would have left behind a highly turbulent and magnetically complex environment. The hypothesis posits that some of this magnetic turbulence, this primordial cosmic stirring, persists to this day near the heliopause. If this is true, it would mean that the local interstellar medium we are entering is not as uniform or predictable as we once thought. It would be a leftover echo of a violent cosmic past, a swirling memory etched into the very fabric of space. If this hypothesis holds true, it also suggests a fascinating possibility for the future of the Voyager probes. As they travel further away, deeper into this ancient, turbulent region, they will likely encounter a different magnetic orientation, a true shift that aligns with the galactic magnetic field once they have left the immediate magnetic echoes of those long-ago supernovae behind. However, there's a quiet, poignant truth that accompanies this thought. Their instruments will probably be long dark by that time. The universe, it seems, will keep some of its deepest secrets just beyond the reach of our current explorers, inviting future generations to build even more resilient and longer-lived messengers. The combined findings from both Voyagers, the unexpected constancy of the magnetic field, and the unchanging distance of the heliopause despite solar cycle variations, paint a picture of a far more intricate and resilient boundary than previously imagined. It's a boundary that holds its ground, not just physically, but magnetically, resisting the simple ebb and flow of solar activity. This challenges us to think differently about how our solar system interacts with the galactic environment, suggesting that the interstellar medium itself might be more structured, or that the interaction is governed by principles we are only just beginning to grasp. These profound discoveries from two small aging probes highlight the incredible power of direct measurement, the quiet persistence of instruments that were never truly meant to last this long. They are reminders that the universe is not just vast, but also endlessly surprising, always ready to reveal another layer of complexity, another subtle dance of forces that reshapes our cosmic understanding. The Voyagers, in their gentle, unwavering journey, continue to be our humble teachers, whispering profound truths from the very edge of our known world, pushing the boundaries of our knowledge in ways we could never have foreseen. They are living testaments to the fact that curiosity, when coupled with ingenuity and persistence, can unlock secrets whispered from billions of miles away. Let us now delve deeper into the quiet whispers that the Voyagers have been sending back from the cosmic frontier. The specific details within their data that have so profoundly reshaped our understanding. These aren't just grand sweeping revelations. They are the subtle shifts, the unexpected hums, the precise measurements that speak volumes about the true nature of interstellar space and our solar system's interaction with it. Each faint signal traveling across billions of miles carries within it a piece of a grand cosmic puzzle painstakingly assembled by dedicated scientists here on Earth. One of the most critical elements the Voyagers were designed to measure, particularly as they approached and then crossed the heliopause, was the population of galactic cosmic rays. Imagine these as tiny, incredibly energetic bullets fragments of ancient cosmic explosions from across the Milky Way, zipping through space at nearly the speed of light. Here within our heliosphere, our sun's magnetic field acts like a gigantic protective shield, deflecting most of these incoming cosmic rays. It's like standing under an invisible umbrella during a hailstorm. You hear the patter, but you're largely protected from the direct impact. What Voyager 1 and later Voyager 2 observed was a dramatic and sustained increase in the count of these galactic cosmic rays as they pushed beyond the heliopause. This wasn't just a slight uptick. It was a clear and undeniable surge. It was the direct, incontrovertible evidence that they had finally escaped the sun's magnetic umbrella and were now truly exposed to the raw, unfiltered cosmic environment of interstellar space. Imagine stepping out from under that umbrella into the full force of the hail. The sudden rush of impacts tells you exactly where the shelter ends. This profound shift in cosmic ray flux was one of the primary indicators, along with the plasma density changes that signaled their epochal crossing. The data allowed scientists to precisely measure how effective our heliosphere is at shielding us and to understand the unfiltered cosmic ray environment that future interstellar missions, or perhaps even human explorers, would need to contend with. Beyond the cosmic rays, the probes were equipped with plasma wave detectors, sensitive antennae designed to listen to the vibrations and oscillations within the charged particles of space. Think of it like listening to the subtle hum of a vast electric ocean. These plasma waves are generated by the movement and interaction of charged particles. As Voyager 1 crossed the heliopause, its plasma wave detector picked up a distinct, almost ethereal increase in plasma density, as we touched upon earlier. This wasn't just a guess. It was a precise measurement of the frequency of these plasma oscillations. The denser the plasma, the higher the frequency of the waves it supports. Voyager 1 essentially heard a change in the pitch of the cosmic hum, going from a lower tone in the heliosheath to a much higher, denser tone in interstellar space. This wasn't an immediate dramatic change, like flipping a switch. Instead, it was a gradual yet unmistakable shift over a period of time, revealing the subtle transitions at this boundary. The detailed analysis of these plasma oscillations provided crucial insights into the density and temperature of the interstellar medium itself. How thick it is, how warm or cold its particles are. It was like taking the precise temperature and pressure of a new vast atmosphere. These subtle shifts in plasma oscillations are invaluable because they are direct measurements of the medium itself, telling us about its fundamental properties, properties that were previously only inferred through indirect astronomical observations. The Voyagers were truly tasting the interstellar wind for the very first time. The importance of long-term data collection cannot be overstated in this saga. The Voyagers weren't just sent out for a snapshot. They were designed for an extended, persistent watch. This long-duration data collection spanning decades allowed scientists to reveal trends and anomalies that would have been impossible to predict or even detect from shorter missions. Imagine trying to understand the climate of a planet by observing it for just a few days. versus monitoring it for 40 years. The long-term data from Voyager has allowed scientists to see how the heliosphere itself breathes and interacts with the interstellar medium over multiple solar cycles, even if some of those interactions, like the heliopause distance, surprise them with their consistency. This continuous stream of information also allowed for the detection of subtle, long-term changes in the interstellar medium that would otherwise be invisible. For instance, the probes have been able to provide data on how the interstellar magnetic field gradually changes over vast distances, giving us clues about the broader galactic magnetic landscape. These long-term trends are like listening to the slow, deep currents of a vast ocean currents that shift over months and years, revealing the subtle ebb and flow of cosmic forces. And then there's the beautiful, almost poetic human element in interpreting this data. Imagine the scientists years after the launch poring over these faint signals from billions of miles away. Each blip, each subtle shift is a whisper from the edge of knowledge. It's a testament to their dedication, their patience, and their profound intellectual curiosity. They are the cosmic detectives piecing together a story told in electromagnetic waves, translating the universe's silent language into human understanding. This isn't just about reading numbers. It's about deep interpretation about hypothesis and rehypothesis about the relentless pursuit of truth across unimaginable distances. The human ingenuity that built these probes is matched only by the human persistence required to listen to their whispers for decades. The profound impact of this wealth of data on our understanding of the sun's sphere of influence, the solar system's true extent, and the local interstellar medium is almost incalculable. Before Voyager, our map of the solar system ended conceptually somewhere around the orbits of the outer planets. We knew there was something beyond, but it was largely a blank canvas populated by theoretical models and educated guesses. The Voyagers have filled in that canvas with rich empirical detail. They've shown us the precise pressures, the temperatures, the densities, and the magnetic configurations of the heliosheath and the interstellar medium. They have provided direct measurements of the cosmic rays that bombard our solar system from distant supernovae, informing us about the radiation environment that future interstellar travelers would face. They have revealed the complex, bubbly nature of the heliosheath, showing us that our cosmic shield is far more dynamic than we imagined. They have measured the interstellar magnetic field directly, giving us our first ground truth data on the magnetic environment outside our sun's domain, even if it puzzled us initially with its consistency. Think of each data point as a faint whisper from the edge of knowledge, piecing together a grand cosmic story. It's like receiving fragments of an ancient forgotten text and slowly, painstakingly putting them together to reveal a narrative far more intricate and compelling than any single fragment could suggest. The Voyagers are not merely sending back numbers. They are sending back the raw material for a deeper, more profound narrative of our place in the cosmos. They are showing us not just what is out there, but how our solar system truly fits within the vast interconnected tapestry of the galaxy. The very act of gathering this unprecedented wealth of data, this continuous stream of quiet revelations, has humbled us in the most beautiful way. It has shown us that the universe is constantly rewriting our textbooks, inviting perpetual learning and a profound sense of wonder. The initial theories were good, necessary starting points, but the universe itself always holds the ultimate truth, and it speaks that truth through the persistent, almost miraculous voices of these distant probes. The Voyagers have become our ultimate truth-tellers, challenging our preconceived notions and guiding us toward a more complete and infinitely more fascinating understanding of the cosmic ocean we inhabit. Their scientific legacy is not just about breakthroughs, but about the ongoing patient and humble dialogue between human curiosity and the vast speaking universe. Let us now shift our perspective from the immediate scientific revelations to the grand, almost unfathomable future of the Voyager probes as they continue their silent, solitary journey long after their active mission concludes. Although the historic Voyager mission in its operational sense will soon be ending, its gentle power source slowly dimming, its instruments gradually falling silent. The twin probes themselves are truly just beginning their cosmic journeys. They are not simply turning off. They are embarking on an eternal drift, propelled by the very forces they helped us understand, becoming silent time capsules cast into the boundless ocean of the Milky Way. Imagine these small intrepid probes as tiny enduring seeds carried by the cosmic winds, destined to sprout into new understanding, far beyond the grasp of human observation. In approximately 40,000 years from now, a blink in geological time and eternity in human history, Voyager 1 will likely drift towards a star in the constellation Ophiuchus. It won't reach this star, nor will it truly visit it in any observational sense. Instead, it will merely pass by, a silent, unseen speck of human ingenuity, making its nearest approach to another sun a moment of cosmic anonymity in the vastness. 40,000 years from now, our civilizations might be vastly different, perhaps even unrecognizable, but the little Voyager 1 will still be out there quietly moving towards its rendezvous with a distant star, a testament to a long-forgotten age. Its twin Voyager 2 will embark on its own equally profound, yet different trajectory. In a staggering 296,000 years, it will pass a mere 1.7 light-years from the star Ross 248. 1.7 light-years. That is a distance so immense it defies our terrestrial comprehension. Yet for a probe traveling for nearly 300 millennia, it's merely a close flyby. And even further into the unfathomable future, in an astonishing 296,000 years, it will pass 4.3 light-years from Sirius, one of the brightest and most familiar stars in our night sky. Imagine that a tiny fragment of humanity, having endured for hundreds of thousands of years, quietly sailing past a star that still twinkles brightly in our future skies. These are not active scientific missions anymore. These are profound acts of cosmic navigation, propelled by the enduring momentum they gained so long ago, forever tracing paths through the galactic tapestry. The contemplation of these timelines leads us to a truly humbling thought. These small intrepid probes, these silent metallic wanderers, will likely outlast the Earth itself. Our planet, vibrant and alive as it is, has a finite lifespan. In billions of years, our sun will expand into a red giant, likely engulfing or sterilizing Earth. But the Voyagers with no atmosphere to succumb to, no oceans to boil away, no tectonic plates to grind, will continue their solitary wanderings. They are cosmic time capsules, destined to endure for eons long after the human species has perhaps evolved into something new, moved to other star systems, or simply faded into the cosmic dust from which we came. They are the ultimate enduring monument to our transient existence, a silent echo of a curious civilization that once flourished on a pale blue dot. As they continue their solitary wanderings, these tiny emissaries will gently cross the vast expanse of the Milky Way galaxy. Our galaxy is a spiraling island of hundreds of billions of stars, and the Voyagers, though moving at tremendous speeds by human standards, are merely drifting at a snail's pace on this grand galactic scale. Their journey across the Milky Way will take millions upon millions of years, but they will carry with them, etched into their very being, a silent record of where they came from. And here lies the most fantastical, yet deeply poignant possibility: if by some unfathomable chance they encounter intelligent life in one of the far reaches of our galaxy, billions of years from now, they will not arrive empty-handed. They will not be mere inert chunks of metal. Instead, they will be a profound testament to mankind's ingenuity and resilience. They carry within them a message, a whisper across the eons, designed not for scientific data, but for connection, for introduction, for a shared sense of cosmic companionship. This message is embodied in perhaps the most iconic part of the Voyager probe's legacy, the golden audio-visual disc, famously known as the Golden Record. Imagine on each of these probes, securely fastened and protected, rests a 12-inch gold-plated copper phonograph record. This is not just a storage device. It is a carefully curated anthology of humanity, a message in a bottle cast into the vast cosmic ocean. These golden records carry a profound summary of our existence. They contain photographs of Earth and its many life forms, vibrant images of our planet's landscapes, its flora and fauna, the diversity of its people. They capture the sounds of whales singing their ancient songs across the oceans, the universal cry of a baby being born into the world, the thunder of a volcano, the gentle whisper of wind through leaves. They hold music by Mozart and Chuck Berry, a testament to the diverse artistic expressions of humanity. Bridging classical elegance with rock and roll exuberance, and they contain music from dozens of indigenous peoples from around the world, showcasing the rich tapestry of human culture and tradition. Finally, they include greetings in 55 different human languages, a collective hello from every corner of our planet, a chorus of voices reaching out into the silence. This golden record is more than just data. It is a profound act of hope. It is a time capsule filled with the essence of who we are, a gentle poetic attempt to communicate across unimaginable distances of space and time. It would offer a distant alien stranger, if they were ever to find and understand it, a glimpse of who we are and what life on Earth is like. It's a message that transcends language and culture, appealing to universal concepts of life sound and natural beauty. Imagine the wonder, the profound sense of connection if such a record were to be discovered by another intelligent civilization, eons from now. It would be a handshake across the cosmos, a silent dialogue spanning billions of miles and millions of years, proving that life in some form once existed on a small pale blue dot. The golden record is not about answers, it's about questions. It asks, is anyone out there? Are we alone? And it answers. We were here. We were curious. We created beauty. We sought to understand. It is a testament to the very best of humanity, a quiet, enduring symbol of our collective spirit, our yearning for connection, and our boundless capacity for wonder. This legacy, this silent, enduring journey, reminds us that while our lives here on Earth are fleeting, our dreams and our creations can soar to unimaginable distances, enduring for lifetimes far beyond our own. The Voyagers are not just machines. They are the physical embodiment of our dreams, our hopes, our most profound questions launched into the cosmic unknown. As we gently drift back from the far reaches of interstellar space, having contemplated the profound journey and the silent future of the Voyager probes, a sense of bittersweet reflection settles upon us. Although the historic Voyager mission in its active operational phase will soon be ending, its gentle, persistent whisper growing fainter, its final data packets slowing to a halt, the very thought carries a quiet dignity. We must, in a way, say goodbye to these old familiar friends. These probes for nearly half a century have been our eyes and ears at the very edge of the cosmic ocean, patiently sending back postcards from realms previously unimagined. They have been steadfast companions in our collective journey of discovery, silent witnesses to the universe's grand design. But this farewell is not one of sorrow, but rather of profound gratitude and a quiet sense of accomplishment. Their mission for us here on Earth has already achieved far more than anyone could have dared to dream. And now, as they continue their lonely, unending drift, we must in turn continue our own lives here on Earth, enriched by the knowledge they have gifted us. Their journey reminds us that even as we focus on our daily lives, there is a vast, beautiful, and mysterious universe unfolding around us, waiting to be explored, waiting to reveal more of its secrets. Hopefully, the Voyager mission will not be our last brush with the stars. In fact, it should be seen not as an ending, but only as a beginning. It is a profound proof of concept, a testament to what human ingenuity, persistence, and a boundless sense of curiosity can achieve. It has shown us that it is possible to send our creations beyond the familiar embrace of our sun, to listen to the whispers of interstellar space, and to gather truths that reshape our very understanding of the cosmos. The lessons learned from Voyager about designing durable spacecraft, about harnessing the subtle forces of gravity, about extracting faint signals from incredible distances, will form the bedrock for future, even more ambitious endeavors. Imagine the Next Steps missions, designed not just to cross the heliopause, but to actively explore the local interstellar medium in greater detail, perhaps even to journey to the Oort cloud, that vast icy halo at the true edge of our solar system. Or perhaps one day to send probes not just to another star, but into its orbit, truly venturing into another solar system. The Voyagers have opened that door even if they cannot walk through it themselves. They have shown us that the path exists, and that our dreams of galactic travel, however distant, are not merely fantasy, but a plausible future. The very existence of the Voyager probes, tirelessly operating for decades beyond their warranty, is a powerful symbol of mankind's ingenuity and resilience. It speaks to our ability to dream big, to face immense technical challenges, and to persevere against overwhelming odds. It reflects our innate drive to explore, to push boundaries, to understand our place in the universe. It's the spirit of the ancient navigators, scaled up to cosmic proportions, a quiet yearning to know what lies beyond the horizon, no matter how distant or challenging that horizon may be. This resilience isn't just about building machines that last. It's about the resilience of the human spirit itself, our unyielding desire to learn and to grow. The Voyager probes, in their long silent journey, have also given us a profound gift perspective. When we contemplate that tiny, pale blue dot photograph, our entire world, our entire history, compressed into a single, almost invisible pixel. In the vastness, it whispers a powerful message. It reminds us of the fragility and preciousness of our home, and the shared destiny of all humanity on this one unique planet. It encourages us to look beyond our immediate concerns and appreciate the grand unifying narrative of our existence within the cosmos. It's a gentle nudge towards humility and wonder, fostering a deeper appreciation for the delicate balance of life here on Earth amidst the stark indifference of space. So as the sun sets and the stars begin to emerge, let us carry with us the spirit of the Voyager mission. Let it be a reminder that curiosity is a powerful force, that patience can unlock unimaginable secrets, and that even the smallest of our creations can leave an indelible mark on the vast canvas of the universe. The Voyagers have sailed beyond the known, carrying our hopes and dreams, and in doing so, they have redefined what is possible. For now, these quiet, intrepid explorers continue their solitary wanderings, heading towards an unimaginably distant future where they might be found by another consciousness, a testament to the curious beings who once lived on a vibrant planet far, far away. We bid them a fond, lingering farewell, knowing that their journey, though no longer actively communicated, continues to inspire us to look up, to wonder, and to keep reaching for the stars. Well, that's all we have time for today. Curious minds and sleepy thinkers. I hope you've enjoyed listening to this contemplative journey through the Voyager missions, a quiet exploration of endurance, discovery, and the boundless mysteries of the cosmos. If you like what you've heard, please feel free to gently follow us for more podcasts on other fascinating space topics, allowing your mind to drift into new realms of wonder. But for now, I'm Alex Mulan, and this has been Astron. All the best, and see you next time under the same vast, wondrous sky.